Our today's lecture will be on the third section and the final section of this chapter. We're going to talk about coefficient of determination and further topics in regression analysis. After the end of this chapter, we will be able to deterministically describe the relationship, the significance of the relationship, a quantification of the amount of variability between two variables. So by the end of this section, we will be able to calculate the sum of squares error, SSE, and use the standard error of estimate, small s, as a measure of typical prediction error, describe how total variability, prediction error, and improvement are measured by the total sum of squares, SST. The sum of squares of errors, SSE, and the sum of squares regression, SSR. Explain the meaning of the coefficient of determination R squared as a measure of the usefulness of regression. So let's start one by one. The first one is sum of squared errors. The sum of squared errors, or SSE, is the sum of the prediction error squared, or the residual squared. So from each y data, you subtract the predicted y data, you square it, you add them all, you get SSE. Which is called the sum of squared errors or the sum of squared residuals. The standard error, small s, is given by the square root of SSE over sample size minus 2. And we should not confuse ourselves with capital S, where capital S is the quantity that describes the standard deviation. So capital S is standard deviation, small s is the standard error. Let's talk about the least square criteria. I have mentioned it once that least square criteria is the reason why we were able to do the regression analysis. So what does this say? The least square criteria states that the regression line will be the line for which the SSE is minimized. So what does that mean? That means the standard error gets to be minimized. So this is the best to predict the information. That is, out of all possible straight lines, the least squares criteria chooses the line with the smallest SSE to be the regression line. That's why we call the regression line the line of best fit. The total sum of squares, or SST, is the characteristic that measures the total variability in the values of y. So from each y data, subtract the mean and find the deviation of the data, and you square them and add them. So what is SST? SST is the standard deviation square, or the variance, multiplied by sample size minus 1. Remember, S squared is the variance. If you multiply n minus 1 with it, you get the total sum of squares. This is the capital S squared, where S is the standard deviation. The statistic SSR is called the sum of squared regression, and SSR is the predicted value minus the mean value for each data point y squared and then summed. So for each y, find the predicted value, find the mean, find the difference between the mean and the predicted value and square it and add them. For all y's, you get SSR, sum of squared regression. And there is a very nice relationship between these three. SST is equal to SSR plus SSE. In future, we will need a slight variation of this thing. So if you want to find SSR from this thing, you will say that this is SST minus SSE. So that will give you the value of SSR. The coefficient of determination, which is the most important characteristic of all of these characteristics, is denoted by R squared, which is the ratio of SSR and SST. And it measures the goodness of the fit of the regression equation of the data. We interpret R squared as the proportion of variability in y that is accounted for by the linear relationship between y and x. So how much variation in y is explained by the variation in x is the deterministic property coefficient of determination. And we will learn how to interpret this thing in context, and that will better help us understand this concept. There are computational formulas for SST and SSR, which we're going to totally skip at this point because we know that we're going to do all the calculations in our Excel spreadsheet, and I will show you. So let's start with a problem. This is a problem that you can associate with the holiday season. Remember, in holiday season, we are sending a bunch of gifts to the near and dear ones. And one of the prime thing that we all probably have used once, at least once, is the flash rate box. So what is the concept? It is a size of a box that determines the postage. So it doesn't matter whether you put 2 t-shirts in a box or you put electrical drilling machine in the box. As long as the size of the box has not changed, the postage you pay doesn't change. How we get to do that? How the postal services get to do that? That is what I'm trying to explain using this problem. So it says the table contains the volume x in cubic meters and the weight y in kilograms of 5 randomly chosen packages shipped to a local village. The regression equation is y hat equal to 1.6x plus 4. So what we know so far? Regression equation. So you know the slope, b1 is 1.6, and you know the y-intercept, that is 4. What you want to find is y bar. What is y bar? Y bar is the mean of the y data. So what I will do, I will go to the Excel spreadsheet that we're supposed to use for this section, which is more about regression. And I will show you how this one spreadsheet is going to calculate everything that you need to know about regression. So let's input all the information that we have. And I'm going to go to our problem. The x values that we have are 4, 8, 12, 16, and 20. The corresponding y values in kilograms are 10, 16, 25, 30, and 35. So I want to know what is y bar. If I scroll down, y bar is mu underscore y. So that's the y bar value. It's 23.2. So we already have found the variance, the mean of the y data. It's equal to 23.2. Let's see what else we can do. Compute the residual and the squared residuals for each data value from a table of the residuals and the squared residuals, which is our Excel spreadsheet table. Sum the squared residuals to get SSE. So I'm not going to do all the work. I will show you which are the columns for residuals and squared residuals. Remember, residuals are prediction error. So it's y minus y hat. And y minus y hat squared is the squared residual. So I want these 2 columns. What I do, Control C for copying, and I go to my problem and I paste it and I fit it in. So I have done all the work. I will just fit in this table in the problem. And then it is asking me to find SSE, which is calculated in the spreadsheet already. See, SSE is 5.2, and that answers my question. I'm going to go ahead and say that, well, SSE for this problem is 5.2. Calculate and interpret small s, the standard error of estimate. So let's first use the formula. Small s is equal to SSE over n minus 2. N is 5. We have 5 data points in this problem. So 5 minus 2. And then you take the square root. So if I want to write the formula for our sake of understanding, I will first write n minus 2 here and then put the values in. SSE, remember you found 5.2. Divide by 5 minus 2, which is square root of 5.2 over 3. And then calculate that in your calculator. I'm going to do that. 5.2 divided by 3, and then you take the square root, you get 1.3166. And that is the standard error. I can check my work. Without doing any work, if I looked at my table, the Excel spreadsheet, it will tell me that the standard error is 1.3166. Now, interpretation is something that we will do for the first time. So what we say if the regression line is used to predict the y values, and remember the y values are the weight of the packages, the weight of the packages, then actually I should say a little more, weight of the packages using the volume of the packages. I'll mention the x variable as well. Using the volume, which is the x of the packages, then the predictions are correct up to a certain margin of error, up to plus or minus 1.3166 kilograms. So the standard error basically gives you the margin of error in the prediction. Calculate the sample variance S square. Remember, S square we have seen is equal to n minus 1 times SST. Well, sample variance, you can find it in two ways. One of the ways to find the sample variance is just go to directly to the table, and I see that S square y, because it is asking us to find the sample variance of the y variable, is 103.7. That's what the sample variance is. And the other way, you just use the variance formula and find it. So I'm not going to do that. I'm going to take this value from the table. So we'll say S square is 103.7. Then it is asking you, I'm sorry, I have written this formula wrong here. It should have been SST equal to n minus 1 times S squared. So let me fix it. SST equal to n minus 1 times S squared. And then it is asking me, use S squared to calculate SST. So SST is equal to n minus 1, again it's 5 minus 1 times 103.7. So it's 4 times 103.7. And then you multiply, you're going to get 414.8. Let's see whether I did this what right or not. Every single time I'm showing you the mathematical way of finding it, but always keep in mind, you don't have to do this. You can just go to the Excel spreadsheet and find the value from there. What is SST? Well, SST is 414.8. All right. Use SST and SSE to find SSR. Again, remember the formula. SSR is equal to SST minus SSE. So that will be SST is 414.8 minus 5.2 is SSE, which we did in earlier part of the problem. So SSR is equal to 409.6. Again, I don't have to do it this way. I can go to the Excel spreadsheet and it would tell me the SSR. It's 409.6. Finally, calculate and interpret the coefficient of determination R squared. Remember, coefficient of determination is the ratio of SSR over SST. So you do 409.6 over 414.8. So let's do that. In our calculator, 409.6 divided by 414.8, and I get 0.9875 rounded to 4 decimal places. The interesting part is the interpretation. When you interpret coefficient of determination, there is a unique way of writing it. Not only that, you always change the coefficient of determination to a percentage. How do I do that? Multiply the coefficient of determination by 100 or move the decimal point 2 units to the right. So it is 98.75%. And you write the interpretation as, we say the x variable, so the volume of the box describes 98.75%. So most of the variability for the weight is described by the volume. The volume of the box describes 98.75% of the results of variability of the weight of the box. So what did we learn? We learned that it doesn't matter what we put in the box, the volume is what is going to describe the variability of the weight of the box. And that's how postal services could do it. They can help us send things, ship things with a flat rate. Depends on the volume and the volume solely of the box. Use R squared and B1 to find correlation coefficient R. Well, if R squared, we know that it's 0.9875. To get R, it's pretty simple. You take the square roots on both sides. The problem is, square root will give you two answers. Your R is going to be plus or minus whatever the square root of 0.9875 is. So I will do it in my calculator. 0.9875, take the square root of that. I get 0.9937. But I have two of them. Which one I take? Positive or negative? Well, remember, B1 in this problem is 1.6, so that's positive. Also remember, we talked about it. If B1 is positive, then the correlation coefficient is positive as well. So we get to say, thus, or hence, R is equal to 0.9937. That answers your question. Now, the correlation coefficient and the coefficient of determination, I don't have to calculate. If I show you the Excel spreadsheet, you will see it yourself. The coefficient of determination is 0.9875 and the correlation coefficient R is 0.9937. They're calculated in the spreadsheet already. So we're going to continue this discussion and we're going to go back to the problem that we initiated on our first day of class, which is the comparison between the mean SAT reading score versus the mean SAT math score.